When it comes to engineering, textbooks often assume perfect conditions, but reality, especially with hydrogen electrolyzers, is much more complex. Factors like material embrittlement and thermal stress can turn simple safety assumptions into catastrophic failures. We are operating at the violent edge of material physics. Standard models like the Butler-Volmer equation often fall short, failing to account for catalyst degradation, membrane drying, and the risks of explosive gas crossover. Think of the electrolysis process using a bouncer analogy to control molecular chaos. While we aim for theoretical minimums, the reality involves complex overpotentials and proton conductivity constraints that push our systems to their limits. Efficiency gains come with a trade-off: exponential complexity. From the large footprints of 1930s alkaline systems to modern AI-optimized PEM electrolyzers, the engineering challenge has shifted from simple scale to managing critical thermal and material limits. P&ID diagrams often represent a logic fairy tale, assuming perfect components and instantaneous response. To truly debug a system, you have to look beyond these simplified 2D models and address the real-world operational nightmare. Geometric realization is where perfect logic meets thermal warpage. When you heat materials like titanium and naphthalene to 80 degrees Celsius, their different expansion rates create stresses that can compromise the entire stack architecture. The governing equations we use in engineering are elegant, but they can be misleading. The gap between these idealized models and physical reality is precisely where system failures often hide, requiring smarter corrections. AI surrogate solvers are changing the game, accelerating physics simulations by up to 10,000 times compared to traditional finite element analysis. This speed allows for real-time adjustments that were previously computationally impossible. Welcome to the era of the digital twin. By synthesizing cyber-physical data, we move beyond simple monitoring into predictive prophecy, where an obsessed digital model can identify anomalies before they impact the physical asset. Reinforcement learning offers a robust alternative to traditional PID control. By optimizing for complex objectives and maintaining safety constraints, an RL agent can handle sensor failures and continue operations where standard loops would crash. The habitat, where digital perfection goes to die. Even slight variations in manufacturing, measured in microns, can have massive consequences for contact resistance and performance in the field. When models fail to reflect reality, troubleshooting can feel like working in the dark. Utilizing tools like EIS plots, thermography, and gas chromatography helps us detect threshold violations before they lead to irreversible failure. Generative AI allows us to explore thousands of design variations in hours. This AI-driven topology optimization produces structures that outperform human logic, unconstrained by traditional manufacturing assumptions. We are essentially rewiring the planet's energy metabolism. With a trajectory aiming for massive capacity growth by 2050, the focus is shifting from individual cell optimization to scaling our global energy infrastructure. Managing entropy is a massive economic engine. While the second law is inevitable, through AI-accelerated obsessive engineering, we can manage it. Now, go out and build something that matters.